Welcome to the 10th lecture on parallel programming with OpenMP and MPI. Today we're going to cover a little bit more about MPI, specifically collective communications, and the architecture of distributed memory systems. So what are collectives in MPI? Collectives have a unique property, which is that they require that all ranks of a communicator must call the collective function. That's the primary rule, and it cannot be broken, which means the collectives are a kind of separate communication mode in MPI, totally detached from point-to-point communication, which we have been looking at so far. Collectives come in two variants, blocking and non-blocking, just like point-to-point. And just like with point-to-point communication, blocking variants have the property that the buffer, whatever it is in this particular function, can be reused after the function returns. Since MPI 3, MPI has introduced non-blocking variants of collectives, and with those variants the buffer can only be reused after completion, which must be done using the familiar functions MPI wait, MPI test, and their variants. Keep in mind that although all the ranks of a communicator must call a collective function, these functions may or may not synchronize the processes. Some do by default. For some of these collectives, it depends on the implementation whether or not they synchronize the processes. So it's like a moving target. You don't know actually from the start. And I can't stress this enough. Collective communication in MPI cannot interfere with point-to-point communication. They are completely separate modes of operation, and it's just wrong to assume that it's possible to call a collective on one rank and a point-to-point function on a different rank and expect them to be able to communicate. Just like with point-to-point communication, there are some general rules for collectives too. So first of all, the same rule as for point-to-point applies here, data type matching. So you cannot send one data type and receive a different type on the other end. That's not possible. Collectives have no tags, so this feature is missing in collective communication in MPI, and the count must be exact, which means there's only one message length, and any buffer that is to receive a message must be large enough to hold that message. If you want to categorize collectives in MPI, there are four types. The first one is pure synchronization. The barrier is a typical example here. The second one is data movement. So how do we move data between processes and multiple groups of processes possibly? And here we have broadcasts, scatters, gathers, and all-to-all communication. The third is collective computation. You know such a thing from OpenMP 2, where we had the reduction clause, and similar things exist here. So there's a reduction and other things in MPI. And finally, there are combinations of data movement and computation. For example, if there's a reduction, the result is available on one rank, but if you want it to be available on all ranks, there's a combination of reduction and broadcast. There's one rule that you should keep in mind. There's a general assumption that MPI does a better job at collectives than you trying to do it yourself with point-to-point calls. Of course, anything that can be done with collectives can also be done with combinations of point-to-point functions. However, the general assumption is that the developers of the MPI implementation that you're using did a good job at optimizing these things, and a lot of research has gone into optimizing collectives. So give it a try. Usually it is better than doing it yourself. So let's start with global communication, and the simplest form of global communication is the explicit barrier. Just like with OpenMP, it works as implicit synchronization of all ranks from the specified communicator. So you just call it like that, MPI barrier with the communicator, and of course all ranks wait until everybody has arrived, and then everybody can go on. So the ranks only return from a call after every other rank has called the function. In practice, it's rarely needed, mainly for debugging or probably for cases where several ranks write files to the file system and you have to be sure that all of them have been closed until you can go on, things like that. But in real production programs, the need for using a barrier rarely arises. The broadcast is interesting, however, It sends the contents of a buffer from one rank, which is called the root or the sender, to all ranks. It requires the buffer as the first argument, the count, the length of the buffer, the data type you want to send, the root, and the communicator. So this root is a special rank which functions as a sender. Everybody else who is not root is a receiver in this operation. There are no restrictions as to who should be root. Often it is rank 0, but it doesn't have to be. In our example here, we have a count of 3, which means the buffer has a length of 3. At rank 1, which is root in our case, we have this buffer filled with data that should be sent to everybody else. So this buffer should be broadcast to the other ranks. Now, if this is the situation to begin with, we call broadcast. We have 3 elements stored at the buffer. The data type is Mpi int. The root is 1. Remember, this root argument has to be the same on all processes, on all ranks that call the broadcast. If this is not the case, then there's no consensus about who should be the sender and who should be the receiver, so it must be the same everywhere. After the broadcast, this is the result. On the sender, the buffer still has the same contents, and the buffers on the receiver sides have copies of the sender buffer, which means in the Mpi broadcast call, the buffer is a receive buffer on all ranks except the root, where it is a send buffer. Scatter is like a sophisticated variant of broadcast, and it works a little bit differently. So scatter is for sending the ith chunk of an array to the ith rank, which means it has send and receive arguments. So a send buffer, a send count, and a send type, a receive buffer, a receive count, and a receive type. There's a root process, again, which is singled out, we'll come to that, and the communicator. In general, the send count and the receive count should be the same. So this is the length of the chunk of data that is to be sent or received. The send buffer is ignored on all ranks which are not the root because there is nothing to send. So anybody who's not a root sends nothing, they only receive. So send buffer doesn't have to have a sensible value there. But you still have to provide it because it's a global, it's a collective call, and everybody has to call it. Everybody has the same list of arguments, so you have to give it a value, but it's not used for anything. Here's an example. Our root again is rank 1, and we have this array of integers 1, 2, 3, 4 at the root, and this array should be distributed to the receiving ranks. So the 1, the first element, should go to rank 0, the 2 should go to rank 1 locally, the 3 should go to rank 2, and the 4 should go to rank 3. We call Mpi scatter with the send buffer, which only has a meaning on the sender, on the root. The send count is 1. So this is not the length of the whole array, because it's implicitly understood that the length of this array is equal to the chunk size, or the count, which is here specified as 1, times Mpi comp size. So here, the length of the subarray to be sent is 1. We're sending integers, then the receive buffer, which has a meaning on sender and receiver sides, because on the sender, we're copying locally a part of the send buffer to the local receive buffer. We're receiving integers, of course, and the root is 1. This is the final result after Mpi scatter returns. Now, every rank has its part of the original array, which was originally stored at the root. The gather is exactly the opposite of the scatter. It receives a message from each rank and places the ith rank's message at the ith position in the receive buffer. Again, it needs send and receive type arguments, so send buff, send count, send type, and send receive buff, receive count, and receive type, and a root. Again, in general, send count and receive count are the same, and now the receive buffer is ignored on all non-root ranks because those ranks do not receive anything. So here we have an example. Each rank has a send buffer. In this case it has length 1. That's why the buffer length arguments here are both 1. The data type is integer, everybody has to supply arguments for send buffer and receive buffer. We have to say something about that later, so there's an optimization or a special option that lets you simplify things in this respect. Only the receive buffer actually needs something at this place, and it needs a buffer which is long enough to hold all the accumulated data from the other ranks. After the gather returns, of course the send buffer contents are the same as before, and receive buffer is now concatenated data received from all the other ranks. Now scatter and gather have the property that the chunk sizes, so the amount of data that's received from every rank in gather or that's sent to every other rank in scatter is always the same. So these chunks are always the same length. Scatter V gives us a little bit more flexibility in this respect. It can send chunks of different sizes to different ranks. For that, we need, of course, some more complicated arguments in this call. So we need a send buffer, which is relevant for the sender only, so the root. Send count is an array specifying the number of elements to send to each rank. So rank I gets send counts of I elements, and the contents of send counts, they could be different for every I. So this is the unique property of scatter V. These chunk sizes can be different. There has to be an array of displacements. That's an integer array specifying the displacements in send buffer from which to take the outgoing data to each rank. And these displacements are like the starting indices of these different chunks. And then of course we have send type, receive buffer, receive count, and receive type, root and communicator. Here's an example. Our root rank is 1. We have an array like this. I tried to color code the different chunks here. So overall we have 4 ranks, and the 4 ranks correspond to the 4 chunks in this array. The first chunk has a length of 1. The second chunk has a length of 3. The third, length of 1, and the fourth, a length of 2. These 4 chunks should now be sent to the 4 ranks, but not in the order in which they are originally stored at the root rank, but in reverse order. So the last chunk should be sent to the first rank, the next to last chunk to the second rank, and so on. Which means the send counts array is sorted in a way to reflect that order. So the first chunk to be sent has a length of 2. This corresponds to those 2. The second chunk a length of 1. This is this element, and so on. Just as the same applies to the displacements array. The first chunk to be sent, the one that should go to rank 0, has an index of 5. So the first element of the displacements array is 5. The second element is 4. So this pointer, this index, points to the chunk of size 1, which has a content of 5 here, and so on. So this is the starting point of the scatter V call. On the receiver side, of course, the receivers have to keep local receive buffers which are large enough to hold the respective chunk sizes that are to be sent from the sender. And of course they have different receive counts since the chunk sizes are different. After scatter V returns, this is a situation. We have the last chunk, which was originally the tail of the array on rank 0. This was sent to rank, which was the tail of array on rank 1. This was sent to rank 0. This single element at index 4 was copied locally on the root to the receive buffer and contains 5, and so on. So you see there's a lot of flexibility here. It's in no way necessary to keep the original order that was prescribed in the original send buffer at the root. And also these different chunks at the send buffer could be overlapping. So the displacements and send counts could be such that different chunks to be sent to different ranks are overlapping each other. That's not forbidden. If there's a scatter V, there should also be a gather V, and there is. Gather B is like a more flexible gather, and it's exactly the opposite of scatter B. It has a receive counts array that specifies the number of elements to receive from each rank. So receive counts of I, that's the number of elements to receive from rank I. Displacements is an integer array specifying the displacements where the received data from each rank I is put into the receive buffer in units of the elements. Now, the all-gather call is a combination of gather and broadcast. So it needs the arguments from gather, and it needs, well, what it does is gathers everything at the root, or at least you can imagine it like that, and broadcasts it again to everybody else. But there is no root argument. There doesn't have to be, because the all-gather, it's implied that every rank in the end gets the full buffer that has been received from all the other ranks. Now you might ask, why do I not just use a gather followed by a broadcast if I want the result of a gather to be available in all ranks? You could do that, but using the all-gather, the MPI library can leverage a lot of internal optimizations that you would have to implement by hand if you did it as a sequence of gather and broadcast, or even as a sequence of point-to-point calls. So again, there's this general assumption that combined collectives like all gather are faster than using separate ones like gather and broadcast. As you might have imagined, there's also a flexible variant of all gather V, which corresponds to gather V and can handle different chunk sizes per rank. So here's how all gather works. We have, in this case, a buffer of size 1 on each rank, and the send count is 1. The receive buffer on every rank must be large enough to accommodate the accumulated size of all received data. In this case, it's 4 integers. And the receive count is 1, of course. After all gather returns, this is the result, everybody has a copy of the gathered data from all ranks. Now, of course, for the general functionality of this, specifying a root is not required. You don't know what happens internally. Maybe the MPI implementation chooses to implement all gather as a gather followed by a broadcast, but it's not necessarily so, and actually there are more efficient ways to do it. And the hope is that the implementers of the all gather know about that and provide a better optimized implementation than just all gather followed by broadcast. MPI all-to-all is probably the most comprehensive or complicated call that you have in MPI for communication. It sends the ith chunk of an array to the ith rank for all ranks. So in a sense, as you will see in the example on the next slide, it's some kind of global matrix transpose. It has to be given send buffer and receive buffer arguments. So send buffer, send count at send type, receive buffer, receive count at receive type. There's an MPI all-to-all V, which allows the chunks to be of different size. So a different number of elements can be sent and received by each rank. There's also an all-to-all W, which allows also different data types and displacement, so very flexible. Let's look at all-to-all. So here's the starting situation. We have a buffer of size 4 on every rank with different contents in this case. The send count is 1 and the receive count is 1. There's a receive buffer of the same size on every rank. Now the way we can envision this is that every rank executes a gather for the ith chunk of each of the other ranks, if this rank is I. So in this case, the array stored at rank 0 was 0, 1, 2, 3, and this data gets scattered across all the ranks into the first slot of the target array, 0, 1, 2, 3. Or you could view the other way around. Rank 0 executes a gather and gathers the first chunk of all the other ranks into its local receive buffer, 0, 4, 8, 12, 0, 4, 8, 12. Rank number 1, the second rank, does the same. It executes a gather operation, but now on the second chunk of each rank, which means it gets the second element of each of those arrays, 1, 5, 9, 13. So that's 1, 5, 9, 13, and so on. So another way to look at this is if you envision these arrays as part of a matrix, and these are the rows of the matrix, then what you end up with in the received buffers of those ranks is like a transposed matrix. Now, so far we've been looking at global communication only, so there was no calculation, no computation involved in these operations. And now we're dealing with global operations. The most important kind of global operation is the reduction. You know this from OpenMP. The general thinking is that we have partial results on all threads, or in this case ranks, and that there should be a designated rank on which all the results should be collected using a predefined operator to tie them together. So Mpi Reduce needs a send buff argument, which is relevant for all ranks, a receive buff, which is only relevant on the root process, of course, a count, because you can do this reduction operation on arrays of data, a data type, and most importantly, an operator, which tells us what to do with the data, and a root where the data, the result should be collected. So the operation is encoded in this operator is performed on all count elements of an array. So that's what it looks like. In this case, we have 4 ranks. Each has a local buffer, a send buffer, and then the count would be 4. We call Mpi Reduce with a count of 4, and in this case, an operator of Mpi Max. I'll come to the options we have here for this operator in a little bit. And then what it does 4 maximum operations, because the length of the buffer was 4 elements, and these 4 maximum operations are across ranks. So what we get is 4 maximum results, and those are put into the receive buffer on the root process. Now, of course, there's sometimes the case where all the ranks require the result. This is not an issue with OpenMP because we have shared memory. Once you put the result into a variable, it's immediately available to all ranks because it's necessarily a shared variable. But in MPI, we have to specify that. And of course, you could have executed an Mpi Reduce followed by a broadcast. But again, it's a better idea to use the built-in Mpi All Reduce function for hopefully better performance. Now, there are 12 predefined operators that you can use here in this place for this operator. There are functionalities in MPI to create your own operator, which I'm not going into here. These are the predefined operators for global operations. So sum, maximum, product, minimum, bitwise operations and or XOR, logical operations and or XOR. And there's even 2 functions that let you obtain the maximum and the position of the maximum, and the minimum and its position. Keep in mind that MPI assumes that all operations are associative. So as you know, floating point operations on real computers are not associative because of round of errors. So you need to be aware that depending on the number of MPI processes and the implementation of these reduction operations, you could end up with different results. Now, I already mentioned that sometimes it may be necessary to supply a buffer argument where actually it's not actually needed at this place. So we have covered a couple of calls where one of the buffer arguments is not needed for anything. You could supply a null pointer, for example. And so this is one solution, but there are also cases where the local input buffer should be overwritten with a result. So sometimes you need 2 buffers, and the global operation requires a copy at the root rank, for example. Now, this could be optimized by telling MPI we don't want that, and that the local operation should not take place, that the receive buffer should be the same as the send buffer. And this is what the in-place buffer specification is for. So here's an example with Mpi Reduce. In Mpi Reduce, we need a receive buffer and a send buffer. Here the receive buffer is at root, total sum. The send buffer is the partial sum, which is relevant for all other ranks, including the root. So in this case, we have a partial sum for all ranks, including root, and a total sum only at the root. Now the point here is not that we have to provide some space for the total sum on all ranks. The point here is that we do want to accumulate into the total sum also at the root process. Now below here we see the option we have for the in-place buffer specification. Instead of calling Mpi Reduce with a separate partial sum and total sum arguments, at the root we can specify Mpi in place for the partial sum. So the send buffer is not actually specified. Instead, we give it a special symbol which has a value that has a special meaning in Mpi, and the library knows that we want an in-place buffer specification. And what happens here is that the local result is not taken from some other variable like partial sum up here, but already from the target variable, total sum. Of course, this only makes sense for the root process. Everybody else needs its partial sums, so here we have the normal way of calling the reduce function. Here's an example with Mpi all reduce. Again, you want to avoid having to specify two buffers at every rank. Actually, it makes more sense with all reduce than with reduce, because with all reduce, all Mpi ranks are the same. There's no special rank like in Mpi Reduce. We don't have to do this distinguish between root rank and non-root rank. So for Mpi all reduce, this can be simplified with the Mpi in place specification by just assigning the partial sum to total sum and then just using total sum as the only buffer in this operation, which means the complete all reduce operation is done using one buffer only. Now that doesn't look like much if it's just a single integer variable, but imagine it could also be hundreds of megabytes of data, and then this may very well be relevant to save space. For reference, I've put here an Mpi in-place cheat sheet and what the in-place specification means for all the Mpi collectives we've covered so far. I will not go into details here. You can also look it up in the standard. So here you see that if you specify Mpi in place for an argument for these collective calls, which argument it should be, on which ranks you should specify it, so root or everyone, and what it actually does. This is taken from the Mpi 3 specification. This concludes our coverage of simple Mpi collective communication. Of course, there's always more to say, but this is the basic set that you should know about. So let's wrap it up. Mpi blocking collectives mean that all ranks in a communicator must call the function and they cannot interfere with point-to-point communication. There are communication and synchronization primitives like barrier, broadcast, scatter-gather, and combinations thereof. Global operations do calculations at the same time as communication. We covered reduce and all reduce. If you want to know more about that, there are some more options and you can consult the standard. There is an in-place buffer specification with Mpi in place, which allows you to save space and copy operation in some cases, so that may be relevant if the amount of data you're operating on in such global operations is large. This concludes our coverage of simple Mpi, and before we go into the more complicated aspects of this library, I'd like to digress a little bit and show you a little bit more about distributed memory system architecture, because this is the system architecture we're going to be using Mpi on. Mpi is the only way to actually go to massively parallel computers, because all massively parallel computers are distributed memory computers. So probably you know this simple block diagram or sketch from the introductory lecture. If we think about distributed memory parallel computing, then we can envision it as processors running processes with a local memory, a network interface, and a communication network. Now, even though this is the way that Mpi sees things in its simple-minded world, it's long gone. Okay? Systems like that do not exist anymore. Today, high-performance computing systems are much more complicated. They have a hierarchical structure which means we have a cluster of shared memory nodes. Each node has a substructure because we have CC-NUMA characteristics per node, sometimes even per socket or per package or per chip. And we have multiple cores per CC-NUMA domain. Sometimes it's even a more complicated underlying structure with caches being shared or private to these cores. So this is the world we live in. Unfortunately, the MPI standard has no idea about that, but we have to deal with it on a day-to-day basis if we want to program these systems. Now, of course, such an intricate structure means also that there's not only a single data path between two arbitrary processes in such a system. There's a lot of data paths with different characteristics. Now, we learned about data paths in the beginning when I told you about basic system architecture, and we also learned about the simple Hockney model for data transfer time, which assumes that the time required for transferring a message of length v is composed of a latency part, so like a setup or a waiting time, plus a part where the data flows at the maximum possible rate, so with its so-called asymptotic bandwidth, b. And then the overall communication time is lambda plus message size divided by asymptotic bandwidth. This is the time. Now, commonly, sometimes when we talk about data transfer efficiency, we also talk about effective bandwidth. And the bandwidth is always data volume divided by communication time. So B effective is V divided by TCOM. Now, you've probably done this in the exercises. Here's a simple result from a simple ping pong benchmark on one of the clusters at the University of Erlangen. And it's a simple system topology compared to what is modern today. But still, we have sockets and CC-NUMA domains and nodes with 2 sockets. Each socket has 10 cores. So there is some substructure. And if we're talking about 2 processes sending a message to each other, then we have 3 possible locations, mutual locations that these 2 processes can take. And this is on the same socket. If they communicate, we call that intra-socket communication. They could be on the same node but on different sockets, which would be inter-socket communication. And they could be on different nodes, and then it doesn't actually matter in which socket they're on, and this is called internode communication. What we see here is a plot of effective bandwidth in megabytes per second versus the message length. Now, of course, if the simple latency bandwidth model applies, then we expect in this kind of plot an S-shaped curve where, of course, the effective bandwidth goes to 0 as the message length goes to 0 because the communication time stays finite because of this latency term, but V goes to 0, which means the effective bandwidth must go to 0, and this is exactly what we measure, no matter where those 2 processes are. As the message length increases, we see that the effective bandwidth goes up, and the lower the latency, the faster it goes up. So for intra-socket communication, where the latency is quite low, in the order of hundreds of nanoseconds, you got a steep rise of the effective bandwidth, while for internode communication, where the latency is long compared to the intra-socket case, the rise is less steep and slower. Asymptotically, of course, since for large data volumes the second term in the communication time dominates, we expect an asymptotic value that is equal to the asymptotic bandwidth in the model B. And we see that this expectation is more or less fulfilled, at least if you squint a little. For the internode case, it is anyway. For the intra-socket case, we have this interesting hump, which is easily explained because we have a cache on these systems. And if 2 processes are in the same socket, it means in this system they also can use the shared L3 cache to communicate. And this happens here. So as long as the message is small enough, the MPI can use the socket cache to communicate between those 2 processes. That's why we have this overshoot in this example. But still, I mean, in all 3 cases, the simple S-shaped curve is actually not what we really observe. We have kinks, we have drops, and the reality is obviously more complicated. Okay, so the general difference between these 3 curves is rooted in system topology, who's communicating with whom and where are they. We have so-called protocol switches, where obviously internally the MPI library suddenly decides that after a given or configurable message size, the algorithm should be changed so that probably the asymptotic bandwidth gets higher. So this happens all the time. Actually, this is a rather simple phenomenology. In many systems and many MPI libraries, the phenomenology is more complicated. And of course, we could have contention effects, which are not seen in this simple example because we only have two processes communicating. But if multiple processes communicate with each other, then of course it's unavoidable that the network is a candidate for bandwidth contention. That said, the Hockney model is still useful. It can give us important qualitative insight, and we'll come back to it from time to time in this course. Now, I told you about contention, and one major contributor to contention is the structure of the network that we're dealing with. So how do we characterize networks? Of course, there are many types of networks, and I will show you some in the next couple of slides. But what is a metric that can quantify how good a metric is, or how well it can transfer data? Now, the general metric here is the so-called network bisection bandwidth. It's a metric for the data transfer capability of a system. How do we get it? We cut the network in two halves, hopefully equal parts, and we cut it in a way that cuts the least number of inter-group connections. So we cut it in a way that whatever bandwidth accumulates over these cut connections is the minimum possible bandwidth, but still the two halves should be as equal as possible. So we cut it and we count the accumulated bandwidth of all the connections cut. And this is the bisection bandwidth. Now, of course, if you have a large system with a large network, the bisection bandwidth will inevitably go up, unless you have two disconnected systems which are connected by a single wire. Then this will not be the case. But in general, the bisection bandwidth does go up if you cut any system in two halves and any larger system. So a better metric for system scalability is actually the bisection bandwidth per node. So this is the bisection bandwidth we just described divided by the number of nodes connected to the network. And this is like the overall bisection bandwidth available to each node if everybody communicates with everybody. Of course, this bisection bandwidth number and also the bisection bandwidth per node depends on many things, especially the bandwidth per link. Naturally, if the bandwidth per network link goes up, so does the bisection bandwidth, and it also depends on the network topology. And what's more important, it also depends, its scaling properties depend on the network topology, as you will see. The simplest network topology that you can imagine, and it's actually more popular than you might think, is the bus. A bus connects a couple of agents or nodes and can only be used by one connection at a time. It is shared among all devices, meaning that its bandwidth is shared. It's a single resource. This has pros and cons. Yeah? What about the bisection bandwidth? If you cut a network that's connected by a bus anywhere to get the bisection bandwidth, it's a constant number because you're always cutting a single bus. So no matter how many nodes there are, it's always a single number, BB. If we divide that by the number of nodes, we see that as we enlarge the network, the bisection bandwidth per node goes down with 1 over the number of nodes. So it goes to 0 asymptotically. That's a bad thing. We don't want that. Okay? It's the available network bandwidth per node goes down with 1 over number of nodes. However, there are many examples where buses are used. So diagnostic buses, the old Ethernet network with hubs instead of switches, a Wi-Fi channel at home, for example. That's all examples of buses or bus-like networks. There are advantages, however. A bus is low latency because it's, in a sense, a very short connection between one node or one agent to the other, and it's very easy to implement. There's a lot of hardware available, and also software protocols are simple and can be implemented in no time. So these are the advantages of bus networks. Of course, the disadvantages sometimes outweigh the advantages. The bandwidth is shared, so the whole thing is not scalable at all. There are problems with failure resiliency. So if there's one defective agent, for example, one node that pulls the bus to ground, then everybody else cannot communicate anymore. So a single defective agent can block the entire bus. And finally, something that, well, you may not think about in the beginning is that each agent needs to be able to drive the capacity and inductance of this bus in order to communicate with everybody else. So we need a large signal power per agent. So you need a kind of driver or something at each agent, at each node, in order to be able to drive the cumulative load of all the agents that are actually listening at the bus, because there's no hardware in between that arbitrates these connections and that can provide this buffering functionality. Now, what else can we do? If we look at the other end of the spectrum, so what is the best thing that we can do? We're looking at non-blocking crossbars. A non-blocking crossbar can mediate a number of connections among groups of input and output elements. So on the right, we see 4 input elements and 4 output elements. The data flow is implicitly understood to go from left to right. Okay, so input here, output there. Each of these crossings is actually not just a simple wire crossing, it's a 2x2 switching element. So it can be switched either to a configuration where the left and the top wire is connected and also the bottom and the right wire is connected, or crosswise where their connections top to bottom and left to right. So these are the 2 states of these 2x2 switching elements. Now, if you think about that, it means that it can be that this whole 4x4 arrangement can be used to implement any possible kind of connection from the input to the output nodes. Now, if you fold this arrangement, this 4x4 matrix across this diagonal, then you get a 4x4 non-blocking crossbar switch. So if you fold it, then in and out nodes match, and you have a switching element that can enable communication between 2 pairs of input and output nodes at the same time without any blocking. In this way, we can build n-port non-blocking switches. In this case, it's a 4-port non-blocking switch. And of course, we can use these switches as elements in a cascaded fashion to form hierarchies. So this is the common case. This is what is done in practice. This allows to have scalable communication, however, at high hardware and energy costs, as you will see. So a true crossbar switch, a single non-blocking n-port switch, is rarely used in practice. There have been examples, for example, large vector supercomputers by NEC, but that's not like a common solution we see in current systems. So standard clusters are built with these non-blocking switches as components, but they don't use huge non-blocking crossbar switches. They use hierarchies of smaller switches. So the compute nodes or devices are split up into groups, and each group is connected to a single non-blocking switch, and these switches are called leaf switches. Those leaf switches are connected with each other using an additional switch hierarchy, the so-called spine switches. In some cases, the spine can have multiple layers. They can also be connected directly. If you have small configurations, sometimes you don't need a spine layer. Now, in such switch networks, there is a topology to this network, which means the distance between 2 devices, which means the number of hops in the switch hierarchy that I need to connect from one node to another node, is heterogeneous. So there are nodes which are closer and nodes which are further apart in this hierarchy. The diameter of the network is a metric for that. It's the maximum number of hops required to connect 2 arbitrary devices. So in case of a bus, for example, the diameter is always 1. In case of a non-blocking crossbar switch, it's also 1. But if you have a switch hierarchy with a leaf layer and a spine layer, then the number of hops is at least 2. Now, in a perfect world, we can build fully non-blocking switch hierarchies, which means that if you choose n nodes half disjoint pairs of devices, they can communicate at full speed. So the whole switch hierarchy is able to mediate n-half connections with full speed. Here's an example where this should actually be possible. It's called a fully non-blocking fat tree switch hierarchy. We have a leaf switch layer with 4 switches here. Each single switch is a non-blocking crossbar with 8 ports. And you see that 4 of the 8 ports of each leaf switch are actually connected to nodes, and the 4 remaining ports are connected to the spine layer. Now, this means that the same number of connections that goes to the nodes also goes into the connections to the other leaf switches. This is why it's called fully non-blocking, because the same bandwidth is available into the direction of the nodes as into the direction of the rest of the network. Now, if you cut this hierarchy in half to get the bisection bandwidth, it's the bandwidth of one link, B, which is denoted here with this bar, times the number of nodes half. If we divide that by the number of nodes to get the per node bisection bandwidth, we arrive at B half. And this is a very good result. This is a desirable result. It means that if we build a switch hierarchy like that, the bisection bandwidth per node is constant. So that sounds very good, but there are problems in practice, which we'll touch on a little bit on the next slide. There's a second problem with this kind of setup, and this is that in practice it could become very expensive. It doesn't look like that here, but for realistic setups with hundreds or even thousands of nodes, the switch hierarchy can be a really big chunk of hardware, which is expensive and also uses a lot of power. So you may want to reduce the amount of hardware you have to put into this network in order to reduce the cost and the power consumption. This is possible by building so-called oversubscribed fat tree switch hierarchies. Oversubscribed means that there are more connections to the nodes on the spine switches than into the backbone, there are more connections to the nodes on the leaf switches than into the spine switch hierarchy. However, you need less hardware. In this example, we have 8-port leaf switches. 6 of these ports are connected to nodes, so instead of 4 up here, and there are only 2 ports available into the spine, which means we have an oversubscription of 3:1 spine versus leaf layer. This is of course more cost effective because we need 1 fewer spine switch, so it's cheaper, costs also less power. However, the bisection bandwidth is also lower, and it's generally B, the bandwidth of one connection, divided by 2K, where K is this oversubscription factor. So this is the bisection bandwidth per node. So there's actually something that you have to decide when procuring or building a large system. What is the desired oversubscription factor? Actually, most large HPC systems today are built as oversubscribed fat tree switch hierarchies, at least in the cost-effective sector. A second thing that has to be kept in mind is that resource management, the job placement, is crucial here. Since this network has a strong structure and the connections to the spine are so thin, you want to place parallel jobs that only comprise a small number of nodes, if possible, on a complete leaf switch. So if you have a job that only has 6 nodes, you want those 6 nodes to be connected to the same leaf switch. If you do that, if the resource management, the job management software can do that, then this job will not feel this oversubscribed fat tree switch hierarchy. However, if the resource management software doesn't care or is not capable of doing that, then also small jobs will feel the oversubscription in the network. That's something that's not desirable. Now let's come back to fully non-blocking fat tree switch hierarchies. I told you that it's almost sounds too good to be true, and in a sense it is too good to be true because there's a little bit of a complication here. In this example, we have again a fat tree switch hierarchy. We have 4 leaf switches. The switches are 4-port switches, and we have 2 spine switches. This is fully connected, so we actually expect a fully non-blocking hierarchy. Now, all these solid lines are actual connections, wire connections between the switches, and the dashed and dotted dash lines are communication patterns or topologies. So let's first look at the dashed pattern. The dashed pattern is a collision-free pattern. So whenever nodes communicate in the dashed pattern, for example, 1 with 5, 2 communicates with 6, 3 communicates with 7, and 4 communicates with 8, then none of the solid lines, none of the actual wire connections are oversubscribed. So there's only one connection per actual hardware wire. So that's a collision-free pattern. However, if you change the communication pattern just slightly, the collision-free goes away. So for example, instead of going from 2 to 6 and 3 to 7, so instead of going over here and over here, we change to 2 to 7 and 3 to 6. So 2 communicates with 7 and 3 communicates with 6. Now this means, using the available wire connections, that we have oversubscriptions on these two wires. So what is the consequence? There are communication patterns, even on a fat tree, fully non-blocking switch hierarchy, that lead to contention, that lead to oversubscription of wires, while other wires are not utilized at all. What's the reason for that? The reason is static routing. Static routing means that the path a data packet takes from a source to a destination is prescribed. So whenever you want to communicate from node N to node K, then the path of the package is pre-described. This is done using a so-called routing table. If those routing tables are static, we always have the potential for collisions. And it turns out that if you have a single application only, then routing tables of switch hierarchies can be optimized or patched in order to accommodate the communication structure of a specific application. And that can, if the application is really communication bound, that can really have a big impact on performance and scalability. Now, what can be done about that, short from actually patching the routing tables to accommodate your application, which is not like the usual mode of operation for a cluster? You can have dynamic or adaptive routing, where the network monitors the utilization of data paths and chooses a path for a packet dynamically, depending on which data paths are less utilized. So even in the cost-effective sector these days, this is becoming the norm, fortunately. So we can mitigate collisions by dynamic or adaptive routing. So just to show you what this looks like, here's an example of a non-blocking fat tree switch hierarchy. That's a single, which means single device. You can buy this as a device, a single 288 port InfiniBand DDR switch. The leaf switches in this arrangement have 24 ports. And of those 24 ports, 12 are connected to devices and 12 are connected to the spine layer, which correspondingly consists of 12 switches. So this is the largest configuration you can build with these 24 port leaf switches. And it has 288 ports. If you want a larger system, more than 288 nodes, you have to cascade these switches again to a larger hierarchy. DDR InfiniBand is not the most bleeding edge network topology available in high performance computing, and on this slide I've given you a very coarse overview of what we have today. So there's of course Ethernet. Everybody knows Ethernet. There's 1 gigabit, which everybody has in their laptops, 10 gigabit per second and 100 gigabit per second variants, and even in some clusters in high performance computing settings, people are using 10 gigabit per second if communication is not that important. The dominant high-performance commodity interconnect is InfiniBand, and there have been numerous iterations from SDR to DDR, QDR, FDR, EDR, and the current one is HDR, which supports a wire speed bandwidth of 200 gigabits per second per direction on every wire. So that's significantly larger than commodity and Ethernet, and also the latencies are much lower. So if you buy a standard high-performance computing cluster today, chances are you will get an HDR interconnect. Now, as I told you already several times, fat tree networks are possibly expensive and complex to scale to very high node counts. So either you spend a lot of money, a lot of energy to build more or less non-blocking fat tree switch hierarchy with dynamic routing, or you make compromises in terms of oversubscription, which could be painful in terms of performance. So how do we solve this problem? Are there probably other network topologies that are less expensive but still have favorable scaling properties or communication properties for high performance applications? And there are. We summarize these under the term meshes. Now the word mesh is used differently in different contexts. Here we use it to summarize everything that's not a bus or a fat tree hierarchical network. So, and there are many variants of meshes. We could have n-dimensional hypercubes or toruses and many others, including hybrids of different topologies stacked upon each other. In a mesh, each node is a router. And it's important to note that this is not a non-blocking crossbar. So even if it looks like it, here we have an example of a 2-day torus mesh. It is not a fully non-blocking switch, because data can only flow in these connections. Now, if we only look at these thick connections, we have a square topology, whereas if you also include these gray connections, so if we close the loops behind this square network, we have a torus topology. And incidentally, just by adding these couple of wires, we can double the bisection bandwidth by doing that. So the characteristic of a mesh is that the direct connection is only between direct neighbors of the mesh. Now, of course, in this case, intelligent resource management and routing algorithms are essential. So there must be some kind of resource manager in place that knows how to put processes of MPI programs close together so that they're not forced to communicate over large distances, which is always detrimental in such a network. There are prominent examples of torus structures at very large systems. So for example, the Cray XE and XK series or the IBM Blue Gene. If we look at torus networks, then the bisection bandwidth is the number of nodes to the power of d minus 1 over d, if d is the dimensionality. So for example here, the 2D torus network, d would be 2. And the bisection bandwidth goes like the root of the number of nodes, obviously, which means that, well, the bisection bandwidth per node goes to 0 for large number of nodes. This is bad. So actually, in this respect, it has the same characteristic as the bus network. However, those machines often show good scaling for many codes, because many codes in scientific computing have more or less local communication properties, meaning that one process only communicates with a limited set of other processes, which could then be placed nearby in the torus network to have less impact on the global communication overhead. Another advantage of these networks is the well-defined and predictable bandwidth behavior. So together with intelligent resource management, you might get away with a more or less cost-effective network and still get good performance for many applications. This is why toruses and similar networks are quite popular. So let me summarize some points of distributed memory architecture. The pure distributed memory parallel computer is a myth. It doesn't exist. Today we have hierarchical parallelism on all levels of the system architecture. The simple latency bandwidth model for communication is good for getting basic insights and qualitative insights, but actually unrealistic in practice. We have protocol switches and contention which make the actual communication characteristics more complicated than just this latency bandwidth gain. Finally, we have a large variety of network topologies at our disposal. We have the non-blocking crossbar, which is prohibitive for very large systems. We can combine such crossbars to build fat tree, either non-blocking or oversubscribed fat tree hierarchies, where routing may become a problem, and we can have meshes like toruses, hypercubes, or hybrids of those that make compromises between cost effectiveness and performance.